Chapter 7 is going to deal with organic functional groups. So now we're going to add some heteroatoms to our hydrocarbons and make some more interesting chemical structures. So some questions that we could ask ourselves: why do certain substances such as narcotics produce an addictive and euphoric response? And very similarly, what is the relationship between the structure and biological activity of complex molecules? And so the answer stems from, most of the time, organic molecules containing clusters of atoms that convey characteristic properties. These are called functional groups. One example is an amine group, shown here, where R stands for any type of carbon structure. And that the amine group is present in narcotics and other drugs, and it's responsible for much of their action, mainly due to this lone pair and how it interacts with other substances inside our body. Another example, opiates, which are narcotics derived from the opium poppy, all have related structural elements. Morphine, codeine, and heroin, we're probably all familiar with those terms. You may not have been familiar with the exact chemical formula of them, but as we discuss functional groups more in depth in this chapter, we'll come to realize that these chemical structures here are all very similar, except for small differences outlined in these colored boxes here. So these three drugs share a very similar structural characteristics, except for some small changes, which is why they have very similar biological activity. So we learned what heteroatoms were in Chapter 6. Remember, these make up a functional group, and they are any atom that is not C or H. Primarily in organic chemistry, O, P, N, and S, sulfur, are heteroatoms. And these functional groups define the molecule's chemical and physical properties, such as reactivity, boiling point, melting point. Typically, functional groups are polar. They lend some more dipole, they lend stronger dipole-dipole intermolecular forces to the molecule, potentially have opportunities for hydrogen bonding as well. So they typically will increase the boiling point and the melting point of just a straight hydrocarbon chain. Table 7.2 summarizes the common functional groups. This would be a good table to commit to memory. And I hate saying that because most people's perception of organic chemistry is, oh, it's just a bunch of memorization. And I hope that we learn in this class that it's not necessarily memorization, but understanding of the different ways atoms bond to each other, the different functional groups, and how we can use molecular structure to determine polarity, interactions, functional groups, etc. So table 7.2, though, it would be good to memorize this table. We already know alkenes and alkynes. Aromatic hydrocarbons we also saw, so we're going to introduce alcohols in this chapter. These have an OH group attached to a carbon chain. Aldehydes have what is called a carbonyl group, CO double bond. So do ketones. Carboxylic acids have a CO double bond bonded to an OH. Esters have an OR group next to that CO double bond. Secondary alcohols and tertiary alcohols, they have a different number of carbon groups attached to the carbon bearing the OH, and we'll discuss that further. Phenol is a special type of alcohol. It's an OH bound to an aromatic ring. Ethers, thioesters, amides, primary, secondary, and tertiary amines, these are containing nitrogen. And last, phosphate ester. So we're going to discuss all of these in this chapter, so that can put you on the road to memorizing and understanding this table. But feel free to refer back to table 7.2, both during your reading of chapter 7, the lecture notes here, and certainly when doing your homework and preparing for the exam. So remember that VSEPR theory predicts molecular shape. Is it tetrahedral? Is it trigonal planar? Is it bent? In a saturated compound, all of the carbon-carbon bonds are single bonds, and in unsaturated compounds, some of those carbon-carbon bonds are double bonds, so with two bonds between the carbons. Also remember that long string of rules we learned in Chapter 6, defined by IUPAC, the International Union of Pure and Applied Chemistry. They have the rules that are used in naming organic compounds. We'll use similar sets of rules to name our functional group containing molecules. So we're going to just change those set of rules very slightly. We already know most of them. Just going to be simple changes in order to name an alcohol or a carbonyl species. So section 7.1 deals with CO containing functional groups, which typically are alcohols and ethers. So here we see generic representations of both alcohols and ethers, and see how they stem from water Water is an oxygen surrounded by 2 hydrogen atoms. In an alcohol, we change one of those H's into an R group, and an organic chemist is lazy, and if we have a long hydrocarbon chain stretching away from this oxygen, oftentimes we will abbreviate it to just R. And you could think of that as a generic carbon substituent. And so this is a generic representation of an alcohol. We've changed one H in water to an R group. If we go further and change the other H as well to either equal or different R groups, we get an ether. That's 2 carbons with an oxygen between them. So an ether has an ROR setup, and an alcohol has ROH. And alcohols can be classified in 3 ways: primary, secondary, or tertiary. And in order to do this, we inspect the carbon bearing the OH group. For instance, here, the OH group is right here. The carbon bearing that group is this carbon, and it has 1 R group attached to it, 1 carbon group. That makes it a primary alcohol. If we look at the carbon bearing the OH in the middle example, that has 2 R groups attached to it. They can be the same, they can be different. It's not important, just that there's 2 R groups attached. That makes this a secondary alcohol. 2 R groups, 1 H, secondary alcohol. If the carbon bearing the OH has 3 R groups attached to it, again, they can be identical, they can be different. That is called a tertiary alcohol. So it's good practice to be able to differentiate between primary, secondary, and tertiary. It has to do with the number of carbon atoms on the carbon bearing the OH. So 3 common alcohols. Methanol is a 1 carbon alcohol. It can't be classified as primary, secondary, or tertiary because it has no carbons on the carbon attached to the alcohol. So it's sort of in a class of its own, the simplest alcohol. And it has, as I said, 1 carbon, 3 hydrogens, and an OH group. Here's the ball and stick model. You can see the tetrahedral carbon, the bent the bent oxygen atom. Ethanol is the next more complicated alcohol. It still is very simple. It has 2 carbon atoms. If we look at the carbon bearing the OH right here, we see that it has 1 carbon neighbor and 2 H neighbors. So this is a primary alcohol. And again, we see the tetrahedral geometry for each of the carbon atoms and a bent geometry for this oxygen atom. We could add a second branch and get what is known as 2-propanol or isopropyl alcohol, commonly known as rubbing alcohol. If we look at the carbon bearing the OH here, we see there are 2 carbon substituents and 1 H. So this is a secondary alcohol. And here's the ball and stick model up here. Ethers are, again, different. They have R groups on both sides of the oxygen. Here's the simplest ether called dimethyl ether. Simply has 2 1-carbon groups on either side of the oxygen, 2 methyl groups. And we name it simply by naming the 2 groups as though they were substituents, methyl and methyl. So this is dimethyl ether. This is diethyl ether. This is probably the most common ether used as a solvent in industrial and laboratory settings. 2 ethyl groups on either side of the oxygen, diethyl ether. Remember that ethers are ROR. Clicker question 7.1. 1-propanol shown here is what type of alcohol? So remember that in order to classify the alcohol, we look at the carbon bearing the OH, which is this carbon here. It has a carbon chain attached to it, and it has 2 hydrogens attached to it. So it has 1 R group and 2 hydrogens, and that makes it a primary alcohol. 1 R group right here. Doesn't matter how many carbons there are in that R group. Everything over here is an R group. 2 hydrogens attached to the carbon bearing the OH, primary alcohol. We learned about skeletal line structures in Chapter 6. Remember that when drawing a heteroatom, we always have to draw that in. It can't be implied. And if there's any hydrogens attached to a heteroatom, such as oxygen, we need to draw that hydrogen in explicitly as well. So here we have 1, 2, 3, 4 butanol, or butyl alcohol. And we can show the carbons just like we did with the skeletal line structures of hydrocarbon chains. Just a zigzag chain, the vertices are carbon atoms, and then we can mentally install the hydrogens in the appropriate number such that each carbon has 4 bonds to it. Here at the end we have the O, we have to draw that in, that's the heteroatom, and we have to draw in this H that's bound to the heteroatom. Same thing with an ether, except that we just have an oxygen between 2 skeletal line chains. So here's the expanded structural formula, butanol. And here's the expanded structural formula of diethyl ether. So, in naming alcohols, the first step, just like naming hydrocarbons, is to assign the root. We're going to use the IUPAC rules. The main chain is the longest chain containing the alcohol, just like the main chain in an alkene is the longest chain containing the double bond. Second part is assigning the suffix. Now we have a new suffix to remember. We're going to change the root name, ane, such as butane, to anol, butanol, to indicate that we have an alcohol present in the chain. And then we assign a locator number to the root, indicating the location of the alcohol. We'll number the main chain from the end closest to the OH group, just like we would with a substituent or an alkene. And we'll place the locator number followed by a dash in front of the root name. And we'll assign a prefix if the main chain has substituents. Same way we would with a hydrocarbon. We already have the numbering scheme because we've numbered the alcohol according to where that alcohol is on the main chain. So let's look at this example here. Here we have a little larger alcohol than ethanol or methanol. We see it's an alcohol from this OH group. The main chain has 1, 2, 3, 4, 5, 6 carbons in it, so it gets the root of hexane. We change that to hexanol to indicate there's an alcohol present. Then when we number the main chain, we start at the end nearest the alcohol. It doesn't matter if there's a bunch of substituents over here that would get large numbers. We always start nearest to this functional group. So 1, 2, 3, 4, 5, 6. So we have a 3-methyl group as a substituent, and the alcohol is on the 2 carbon. So we indicate where it is with a 2 in front of hexanol. 2-hexanol indicates an alcohol on the 2nd carbon of a 6-carbon chain. And then just like with hydrocarbons, we write 3-methyl-2-hexanol to indicate the entire name of this compound. And if the methyl group were over here, we'd write 5-methyl. So that this number is less important now because the OH is a functional group. It takes priority over any other hydrocarbon substituent. There are several ways to name ethers, and we're going to focus on the common method of naming ethers. And that's where we simply take each R group as though it were a substituent, change its root to a YL ending, just like we would with a hydrocarbon substituent, methyl, ethyl, and end the name with ether. And we'll use the prefix di if both R groups are identical. So in this case, we have a 1-carbon substituent, that's a methyl group. It's derived from methane. And we have a 2-carbon substituent, an ethyl group, derived from ethane. And we alphabetize them, ethyl, methyl, ether. As simple as that. That's the common way of naming ethers. That's the only way we're going to discuss in this class. A special type of alcohol is called a phenol, and they consist of the alcohol group attached to a carbon on an aromatic ring. This molecule is called phenol, but if there's other substituents off of this aromatic ring, such as over here, it's part of a larger molecule. It's still a phenol functional group. And here we have a steroid called estrone. We can see the phenol functional group is in the lower left of the entire molecule. And so this is a special type of alcohol. It has an OH group attached to an aromatic ring. So while we could label it as an alcohol, if I provided you with a structure and said label alcohols or phenols, etc., more appropriately, we would circle the entire structure here and label it as a phenol. And naming phenols, just like we are naming benzene rings, carbon number 1 is always the carbon bearing OH, and so we count around the ring to minimize the number of the substituent, in this case 4. 4-ethyl phenol is how we name that. So it's very similar to naming simple substituted benzene rings. So we have in alcohols and ethers, we have an OH group or OR groups, and oxygens certainly have lone pairs. And we know from our discussion on intermolecular forces, if an OH bond is present in the molecule, we can have hydrogen bonding as one of the intermolecular forces. So here's an example of ethanol molecules undergoing hydrogen bonding. They have lone pairs on oxygen, they have H's bound to oxygen, so we can get hydrogen bonding between the molecules, very similar to what happens in water. With ethers, though, they can participate in hydrogen bonding from the oxygen point of view, but they do not have any H's in order to participate with an OH bond. So they can form hydrogen bonds with water, right? Water has an OH, or other alcohols. If we mix alcohols and ethers, they can hydrogen bond to some extent. But if we have a pure sample of dimethyl ether, it cannot hydrogen bond with itself because there are no OH bonds present. Also, compounds that have many alcohol groups, such as this sugar called glucose, are very highly soluble in water. So there's a lot of alcohols here, a lot of OH bonds. They can hydrogen bond with water, just like we show these alcohols hydrogen bonding with each other. So the alcohol here can interact with water, so can the other 4 alcohols, making this very soluble in water. And we know that. We know that sugar dissolves readily in water, and this is the main reason. Sugar has a lot of OH groups, and water is composed of OH groups, and so they can hydrogen bond with each other, making them very miscible. So let's look at some practice problems here. Get a practice drawing alcohols. Okay, so we're asked to provide a structural formula and a skeletal line drawing for the following alcohols and ethers. Then we're supposed to indicate which of the 4 compounds we'd expect to be the most soluble in water and explain why. So, structural formula, 2-propanol, derived from propane, which implies 3 carbons. So let's draw 3 carbons in a row. The 2 tells us that the substituent is on the 2nd carbon, and the last few letters of the name tell us the substituent is an alcohol. So we write OH right here. We fill the rest of the carbons up with hydrogens. And we have the skeletal structure, the expanded structural formula. The skeletal line structure is much simpler, of course. We need a 3-carbon chain, 1, 2, 3. We need a substituent on the 2nd carbon, and that needs to be an OH. And we have to draw the H in this case because it's part of the functional group. And that is 2-propanol, that's rubbing alcohol. 1-heptanol. Again, we have an alcohol, it's on the 1st carbon, and hept, H-E-P-T, tells us it's a 7-carbon chain. Here's a 7-carbon chain. OH group on the 1st carbon, nothing else indicated by the name, so we fill the rest of the carbons in with hydrogens. Okay. The skeletal line structure, much simpler, just a 7-carbon zigzag chain. 1, 2, 3, 4, 5, 6, 7. We'll put the OH group off of the end carbon. It doesn't matter which carbon we do, so I'll use the left or rightmost carbon in the skeletal line structure. Here I use the leftmost carbon. These are the same molecule. We can flip them across a line, or a vertical line, and we get the same molecule. That's 1-heptanol. Next one is cyclopentanol. Again, alcohol. Cyclopent means a 5-carbon ring from cyclo, so we draw a 5-carbon ring. And we put an alcohol on. In this case, we don't have a 1, notice, because any place we put the alcohol gets carbon number 1. Before we install the alcohol, every carbon is identical, so it doesn't matter where we put the alcohol. Now we need to fill in the rest of the H's. So you could have chosen a different carbon for your alcohol. That's fine. And we don't bother with a 1, because if there's only one substituent, and it's the alcohol, that has to be on carbon number 1 by definition. Skeletal line structure is much simpler. That's it. And then this one is a little more complicated. Here we have an ether. So we know we have an oxygen with carbon groups on both sides. One of them is an ethyl group, so let's draw that one in. And we'll fill in the H's. And the second substituent is called cyclopentyl, implying a substituent that is composed of a cyclopentane ring. So here's the first carbon of that ring. 2, 3, 4, 5. And my ring doesn't look, well, it looks okay, like a cyclopentane. Then we need to fill in the hydrogens, just like we did with the cyclopentanol. This time the cyclopentane is a substituent. And that's cycloethyl cyclopentyl ether. If we wanted to draw the skeletal line structure, there's the ethyl group. There's the first carbon, second, third, fourth, fifth. We draw a cyclopentane ring attached to the oxygen. And we're given the two structures here. Dopamine and the hormone adrenaline are shown below. Circle and label the alcohol and phenol functional groups. So dopamine, remember that phenol or phenols are alcohols attached to aromatic rings. And so that means there are two phenol functional groups. And we'll draw an arrow there and to there. And then for epinephrine, again, we have the same two alcohols bound to the aromatic ring, so that is also a phenol. I'm just going to draw another arrow right here. But we also have, if we inspect the chain further down, we see this OH group attached to a normal carbon. So that is alcohol. In what way are these two molecules similar? Well, they both have phenols. And both have NH2 groups right here, which we haven't, or I'm sorry, nitrogen groups at the end of their chain, which we haven't discussed yet, but they do have nitrogens. Not identical, but they're both similar because they have nitrogens, then they have two carbons and an aromatic ring. Nitrogen, two carbons, aromatic ring. And so, how are they different? One, epinephrine, has alcohol. That's basically the main difference. And we forgot to do one thing up here. The second part of the question asks, which of the four do we expect to be the most soluble in water? Well, water solubility is helped by having an OH group. So these three alcohols have OH groups. The ether does not. So this one's not very soluble. Let's see if I can spell that right. Okay, and then we have these three alcohols to distinguish, and in terms of water solubility, most of the time it's the fewer carbons the better. So, or the better ratio of O to C in the molecule. Here we have a 1 oxygen to 3 carbons. Here we have 1 oxygen to 7 carbons. And down here in cyclopentanol, we have 1 oxygen to 5 carbons. So the fewer carbons, the more soluble your molecule is. So this one should be most soluble. And that should make sense because when we buy rubbing alcohol at the drugstore, we buy it in 50%, 70%, 93% solutions. And essentially that means 50% of the bottle is isopropanol and 50% is water. That's a percent solution like we discussed in Chapter 5. And that shows us that isopropanol and water are miscible. And because there are 7 carbons here, heptanol is very, very immiscible with water. Same with cyclopentanol. They're not very soluble. But here, fewest carbon atoms. Okay, clicker question 7.2. Of these two isomers shown, ethanol and dimethyl ether, they both have the same chemical formula, but different connectivity, so they're called isomers. Which would you expect to have the higher boiling point? Well, just as we got done discussing, dimethyl ether does not have any OH bonds. It cannot participate in hydrogen bonding very well with itself. Whereas ethanol can hydrogen bond with other ethanol molecules because it has an OH bond. So ethanol has a much higher boiling point than dimethyl ether. I think about 75 degrees C, and this one is below room temperature. This is actually a gas at room temperature. It's already boiled.